Welcome to People Doing Physics, the podcast that explores the personal side of physics of the Cavendish Laboratory at the University of Cambridge. Hello, I'm Jacob Butler from the Outreach Office.
Hi, I'm Vanessa Bismuth from the Cavendish Communications team.
This month, our guest is Dr Sam Gregson, better known as YouTube's bad boy of science. Formerly a Cavendish particle physicist working on the LHCb experiment at CERN, Sam found that he enjoyed finding ways to engage non-specialist audiences with fundamental physics more than submitting himself to peer review, and moved into science communication. The founder of LHComedy, CERN's first ever comedy show, he now runs science education shows that are played in venues as diverse as the Royal Institution and the Green Man Festival. His Hunting the Higgs talk was recently performed for hundreds of school students here at the Cavendish and has been seen by tens of thousands around the world. Alongside this, he blogs, podcasts and regularly posts videos to YouTube covering current scientific stories and in-depth breakdowns of complex particle physics. Today, we'll talk about what drove him to look for the most fundamental building blocks of the universe, why he now subjects himself to audiences of teenagers, and how he feels particle physics research can better make a case for itself. Stay with us.
See,
Thank you so much.
I've got to pick up one thing just as
Jacob
goes. So not submitting himself for peer review. I would argue that submitting myself to audiences of teenagers is far more savage than peer review, but we can revisit that. We can revisit that later.
Well, hi Sam. Lovely to have you. Lovely to have you with us today. Thank you for taking the time. We start every episode by asking our guests how it all started for them. Could you tell us what sparked your interest in science in general and in physics in particular?
Yeah, it's a great pleasure to be here, first of all. Thank you very much. Yes, so I've thought about this quite a lot. And I think I was actually always a physicist. So the first ever toys that I used to play with were, I don't know if anyone remembers, but the old Brio trains with the magnets on the front and the back. And my favorite thing to do with them, my mum tells me, was to turn the magnets around the wrong way, and rather than linking them up and pulling them like most children, was to try and push the magnets the wrong way and make one magnet push the other one around without touching it. And I apparently found this the most amazing magical thing, trying to understand how I could do this, thinking I was some sort of magician. And I think I always loved trying things out, experimenting, trying to understand how the universe worked from a very early age. I also liked that toy, I don't know if anyone remembers, with the different shapes where you had to put the right shape into the right shaped hole. And apparently, again, my mother tells me I used to love spending hours trying to get the wrong shape into the wrong hole, and then getting very frustrated that wasn't something that you could do, or sometimes it was something that you could do. So I think I always had this drive to want to understand how the universe worked, how the world around me worked. And then I just carried that fascination through all the way to, to a degree in particle physics. I also, along the way, had some really, really inspiring teachers. So one in particular stands out, which was Mr. Britton, or Dr. Britton, at Leeds Grammar School. That was my high school up here in Leeds. And he had a catchphrase. He used to have a board in the physics department which says, "Physics is fun." And I think he kind of had it quite ironically at that time. There wasn't a lot of physics outreach at that time, kind of 25 years ago. But he always said physics was fun. And he used to present it in a very fun way. Lots of jokes, lots of demonstrations. He was very, very supporting. And that really helped nurture my interest in physics as well. So I think interest from a very, very early age, and some very nurturing, very inspiring, very fun teachers as well. Kept
Always a good reminder that to remember that it is fun, should be fun. It's complicated, but also fun.
Exactly.
So yeah, it reminds me, one of my lecturers used to have a sign that said, "All physics is a cylindrical teapot," which is probably less entertaining, but more physically accurate, as it's just exponentially decaying sine wave, if you like those.
We physicists like to make our assumptions, right? There's always the meme about the spherical cow. And, you know, most things start off as a point particle. It doesn't matter if it's a person falling down. It doesn't matter if it's a cow running. It doesn't matter if it's a car. They're all particles. And then they become balls. And then we work up from there. And then they're a collection of balls. But we enjoy our assumptions.
Yeah, indeed. Now, you mentioned that you ended up studying physics or natural sciences at the best possible place, which is, of course, here at Cambridge. Now, was this always the plan, or was this something that you sort of stumbled into?
So it's interesting, actually, because I thought, having had that kind of wish to understand how the universe around me worked and playing with those particular toys, I thought when I applied that I might be an engineer. And I actually applied for engineering first of all. And part of that was because of my interests, and part of that was because, as you will know, being at Cambridge, the physics is kind of hidden behind the natural sciences tripos. So you start in the first year I started doing chemistry, physics, maths, and then you focus down in the later years. So the physics, I was like, there is no physics degree to kind of start with. So I ended up applying for engineering. Got in for engineering at Selwyn College, which is just down the road from the Cavendish department in Cambridge. And then people kind of explained to me afterwards, well, you're more interested in doing a little bit more physics. You might have liked the natural sciences tripos a bit more, give you more chance to start broader and then focus down to the physics in later years. And when I kind of had chats with more people, I realized that actually was the way I wanted to go. So called up Cambridge again. Can I switch, please? I would much rather do the physical side of the Natsky tripos. And they said, well, hang on a minute. You didn't have any tests on chemistry when you did your interviews. So down I came back to Cambridge, sat in with Professor Keeler doing some chemistry. I think it was on hydrogen bonding or something like that. I can't remember now, back in the dim distant past. And eventually after an hour he relented and said, okay, you understand some chemistry, you can come for the natural sciences tripos. So I like to tell people that I got in twice, but I probably
quite an achievement.
Yeah, but I probably just messed up the original one. So however you want to take it, in the positive or the negative, that's up to you.
Yeah. And did your interest in particle physics start during this undergraduate, or was that something that came later?
It's an interesting point, actually, because I always thought when I was getting into physics that I would do astronomy. So everyone looks up at the stars, they see the amazing things in the universe. It's very easy to be attracted to that side of things. Obviously, growing up, you see space launches and things like this, very, very exciting. I thought I would end up in astrophysics or cosmology or something like this. But when I got into third year, we started doing particle physics. And what attracted me to particle physics was the fundamental nature of it. You're taking the tiniest building blocks of the universe, you're finding out how they interact with one another, and then theoretically, you should be able to work forward from there and understand everything. And that kind of really scratched an itch from me, going from that really fundamental level and working forwards. And it just so happened in that kind of third, fourth year when I was going through, so this, we're talking about kind of 2007, 2008, that the LHC, the Large Hadron Collider, was really gearing up to turn on at CERN in France and Switzerland, in Geneva. And it seemed just a really perfect kind of alignment of the stars, if you want, going back to the astrophysics, that I was really interested in particle physics. And it seemed if I wanted to go on to do a PhD, that getting involved in particle physics with the turn on of the LHC would be a really interesting thing to do. So I ended up switching off astronomy and moving towards the other end of the spectrum, from really, really long distances to the shortest distances in particle physics.
That's a far stretch from engineering as well, huh? It's quite a journey.
Well, there's a lot of engineering at the LHC, I guess. They have to build things. But
true.
I think what I realized as well when I was going through is I'm not very handsy. Like, I'm not very good at like touching things and making things. And like if somebody said to me like go build a shelf or something, it would be rusty nails and things sticking out, and it will fall down after 2 minutes. That's a little bit of a stereotype of what the engineer does, but I felt like I was more interested in the theoretical side, more interested in the kind of thinking and the concepts, rather than getting my hands dirty in applications. It was a switch, but it was still trying to understand the universe at the most fundamental level, I guess.
And luckily, there's a a cohort of very qualified lab technicians to help with the handsy stuff. One of whom
very-
we interviewed last month. So
Yeah. There's the most amazing engineers, obviously, at the LHC. The first time I went down to see the underground of the LHC, to see the experiment I'd been working on for 2.5 years, getting the data from on my computer, but I had never ever seen existing in real life, and was starting to wonder if it did exist in real life. The first time,
So the magic data tree.
they're just like, yeah, here you go. This is coming from somewhere that you've never seen, but yeah, it's all good. Don't worry about it. As soon as we went downstairs, I was amazed that the thing ever runs. You're just greeted with this amazing wall of cables, thousands and thousands of cables, junction boxes, pieces of kit. Just how it ever runs, I'm still not sure, because these things must be glitching and switching on and off and running into errors and having to be reset all the time. Is the most amazing machine, is the one of the world's biggest and most powerful machines, and just the fact that it runs is an absolute testament to the engineers who work on that project. And now, of course, we're talking about building one that's 4 times as long. So I wish them good luck with that, if that comes to fruition.
So you graduated eventually in Cambridge and in your natural sciences degree, but you didn't go straight into a PhD, did you? You took some time off and went away and did something else before coming back. Do you want to go through, tell us a little bit more about that time?
Yeah, that's right. So I did 4 years in Cambridge. So I did the 3 years of undergrad, and then the master's course, what they call part 2, or part 3. So I did up to part 2 in the 3 years, and then part 3. The kind of master's course in physics. So 4 years of the natural sciences tripos, with basically down to physics at the end. What people might not know about Cambridge is that it's a relatively small place, and the part that the university dominates is an even smaller fraction of that, although it's a huge fraction of the city. But once you've been there for 4 years, I kind of felt like I'd seen a lot of Cambridge. I was doing the same kind of things, going to the same terrible nightclubs, going to the same events. And I felt like I needed a little bit of a break. Cambridge is also a very fast-paced place. So the terms tend to be shorter than at other universities. So 8 weeks, lots and lots rammed in, lots of events, lots and lots of learning, lots and lots of, sessions and lectures. And I felt like I needed a little bit of break. I needed a little bit of a change of scenery. I also needed to pay off a little bit of my student loan, which I'd accrued over the 4 years. So I ended up leaving, and I worked for a low carbon engineering consultancy called Element Energy in Cambridge initially, and then down in London, which got me out of Cambridge, helped me to kind of stand on my own 2 feet in the big city, if you will. And get a little bit of work experience, and just a change from Cambridge, and like I say, pay off a little bit of that student loan. I very much enjoyed doing that. That was kind of, they were quite early into the market of these low carbon engineering consultancies. So advising government about the policies to take to reduce carbon, advising businesses how they could get up to code on new low carbon standards, these kind of things. So I felt like I was doing something different, but also doing something very worthwhile. Obviously, climate change is a huge issue. So I enjoyed doing that for a couple of years, but eventually I always wanted to come back.
Yeah, so that was my follow-up question. What drew you back to Cambridge, and what drew you back to the PhD after, working in the industry?
So you probably want me to say something like having to get up early in London is hard work. So I wanted to come back to PhD, but that wasn't the main driver. So I always wanted to come back. And like I said, the LHC was switching on around that time. So there was huge coverage of the LHC, a great chance to get involved in a PhD where you would actually see the first data from the LHC. So that kind of drew me back. I always wanted to come back, but I did need that kind of change of scenery, I think, after 4 years in Cambridge, a little bit of a reset. So I always intended to come back, but I think it just was the perfect time to come back, was when the LHC was turning on. One of the things that happened when I came back for PhD was a lot of the people who were working in the particle physics department had been doing their PhD on simulated data from the LHC. So They were simulating the data that will come out of the LHC when it's switched on. And people were doing analyses, setting up analysis code on the simulated data, but then feeling a little bit shortchanged because they weren't actually seeing the proton collisions, the real proton collisions from the LHC. So I felt a little bit sorry for them because as soon as I came back, I was kind of the first run that got to see the actual data from the LHC. So a combination of wanting to come back and the fantastic timing of the LHC turning on was really what drew me back to Cambridge at that time.
And how did this compare to your time as an undergraduate? Because obviously you did your undergraduate at Cambridge and you came back to the same buildings to do this doctorate program.
Very, very, very different. So the undergraduate time at Cambridge is very, very regimented. So, for example, when we're doing physics, every week we'll get a question sheet. You take the question sheet on Tuesday, you hand it in on Friday, you have a supervision the next Monday. Then you get the next question sheet on Tuesday. We have a supervision on, you do it for Friday, you have a supervision on Monday again. And this process repeats. So you knew exactly where you needed to be. You knew exactly what you had to do. And if you didn't do it, you got somebody, sending you an email saying, where is this work? What's going on? And keeping an eye on you. When I came back for PhD, that safety net had kind of all gone. It was now make up your own work, make some novel work. Guide your own work, guide your own time. And I found that quite jarring at first, even though I'd been doing it quite a lot down in London. There was always a kind of boss overseeing what you were doing, setting you work. Whereas here, particularly in the first year, because there are other people who are more important than you coming towards the end of their PhDs, you're kind of left to your own devices. So I spent an awful lot of time kind of trying to get up to speed with the LHC code, the LHCb code, learning Python, learning C++ so that I could understand that code, and kind of asking questions about that code and about particle physics that I thought were interesting. Going to lectures in the maths department to catch up on things that I hadn't actually done in undergrad, which were related to particle physics, so like quantum field theory and gauge field theory. But you really had to arrange your own time and be more organized. And initially that was a little bit jarring, but I think it's a very, very important thing for people to go through, because this is what you will have to do when you become a researcher for yourself, if you go on to become a researcher. So it was almost a training process for becoming a researcher. Very jarring at first, but I swam in the end.
And did you find that your time in the real world helped with that at all? Or was it just a case that it gave you time to forget some important integrals and some matrix calculus that you desperately needed?
So that was very much one case. When you come back and you realise that the people who came straight from fourth year remember all of these, all this Feynman calculus that you're like, I did know that at some point. And it does come back quite quickly. So yes, there's a little bit of a hard transition coming back, having to revise some things that you once knew. But I think going away did help a lot because, when I was living away in London, you obviously have to organise your time. This is things as simple as getting into work on time, doing all your washing, making time for this on the weekend, also having some time for socialising, going out, these kind of things. So I think that really helped me to organise my time and just be a more mature, well-rounded individual who could look after themselves and plan their work. So yeah, I think being in the real world really did help that transition. And I think if I'd gone straight from undergrad, it would have been much more jarring, and I think I would have still been a little bit burned out from Cambridge. So I think it was very helpful to take that break, get some fresh perspective, and as I say, come back at a good time to see the first LHC data.
Did you ever consider, it's a side question, but did you ever consider applying for a PhD elsewhere, or was it always Cambridge?
I did consider applying elsewhere, but I really liked the people who were working on these projects at Cambridge. So the supervisor that I came back to, Val Gibson, she was my second year particle physics lecturer, and I very much enjoyed her lectures. So a chance to work with Val was very, very exciting. So when I saw who I could work with, Val was also interested in outreach. So she was very interested in things like getting more women into science as well. So given her interest in outreach and just her amazing particle physics lectures that I'd been in, it seemed like a fantastic chance to come back to Cambridge and work with her. Obviously, Cambridge has its own draw as well. Just the name of Cambridge is fantastic. I think it would be kind of remiss of me to kind of sell that short. So the chance to come back to Cambridge, which is a fantastic institution and a fantastic chance to work with Val, I think was what drew me back to Cambridge. I did consider elsewhere, but I didn't find that combination that I was looking for elsewhere.
So we touched on this a little bit already, but your PhD took you to the LHCb experiment at CERN. Can you tell us a little bit about what you did there, briefly, not going into too many details?
Yeah, we won't go into any complicated integrals and these kind of things. So the LHCb considers the matter-antimatter asymmetry and CP violation. So every particle in the universe, every fundamental particle has an antiparticle. So for every electron, there's an anti-electron. For every quark, there's an anti-quark. But what you might notice is that there's not much of this antimatter around. So every electron we run across is negative. So where are all these anti-electrons? Where are all these positive positrons, these antiparticles of the electron? That is a huge puzzle which has confused people in physics for many, many years. And the idea is that our best models of the universe say that equal amounts of matter and antimatter should have been created in the Big Bang. But during the very, very early stages of the universe, there were some processes that treated matter and antimatter differently. And that created a slight excess of matter over antimatter in the very early universe. These then collide, the matter and antimatter annihilate one another to create light. And we have this very tiny amount of matter left over. So that's the state of the universe we see today. A very tiny little bit of matter left over, which makes the stars, the planets, makes us, and a universe awash with light. So LHCb was interested in trying to work out, are there any differences between a particle and its antimatter counterpart that could explain how this discrepancy was created in the very early universe? And I looked at a particular decay channel of a particle called a D meson, trying to look for differences between its decay rate as a particle and its antiparticle partner. And we didn't find any differences, unfortunately. So we couldn't help explain this matter-antimatter asymmetry. However, we did manage to take the world's most accurate measurement of no CP violation in this channel. So that was very exciting. We helped to kind of enhance the knowledge in this field, I guess, very, very slightly, but not exciting in the terms of winning a Nobel Prize or answering these big questions. But yeah, so CP violation, and we didn't find any, unfortunately.
Yeah, you said something like you found the most accurate measurement of zero with your results, which normally this would be a bad thing, wouldn't it? But how is it different in physics research in your field? So
I guess here, and usually a lot of these null results wouldn't be published, right? So this is also a big problem we can maybe talk about. But in this case, you've essentially narrowed off a decay. This decay doesn't seem particularly interesting. It's not going to produce these huge differences between particles and antiparticles. So you're still making a contribution to the knowledge of the field. And at the time, like I say, that was the most accurate measurement of zero. Now, unfortunately, it's not, because other experiments have kind of gone further. People at the LHCb experiment have gone further when they've got more data, more information, and they've taken my result and expanded upon it. So it was very useful to find out more about that decay and know that CP violation is not hiding in that decay, we don't think, and push the knowledge forward. But yeah, not very exciting in terms of answering big questions. It is useful to find zero when you're doing your PhD, because nobody kind of jumps on you. If you'd found this kind of amazing thing that breaks physics, I think the whole LHCb collaboration would have descended on me and been like, right, check this, check this, check this, check this, check this. And I might have been there for another kind of 3 years after the end of PhD, trying to get this analysis out. But given that we found nothing, given that people before hadn't found anything, it was a kind of what should we say, inoffensive result that not many people kind of jumped on.
Yeah, but a useful zero. So.
Yeah.
Did you have a little sigh of relief when you saw that? Oh.
Sorry, I should be saying no, right? I should be saying I really want to find this amazing new thing. To some extent, it might be nice. That I think that maybe the perfect setup would be to not find anything in the PhD and then immediately find it as soon as you go into the postdoc and you've got the kind of job secured. But yeah, maybe a minor sigh of relief. There's actually a thing in particle physics. So to make sure we're not biased when we're setting up our analysis code, we do a thing called blinding, which means that we set up the analysis code. And in my case, I added a randomly generated number to the final result of the CP violation. So instead of saying 0 throughout the analysis, it said some random number every time I kind of opened the file, just so that I couldn't lead the code to make a number that was far away from 0. And when I removed this blinding at the end, once we'd set up all the analysis code, the answer came out to something crazy, some huge CP violation, like 10%, which was unexpected. And what I realized is that I'd just put minus this number into my code at the end. And actually the random number had been generating a negative number. So I'd gone minus and added on some extra number. So I doubled this offset and made an absolutely crazy number. And it looked like there was huge CP violation in this channel until I realized that I had to delete the modulus of this number from the final answer. And then it went very, very quickly back to 0. So yeah, sad times.
Did you have a brief moment of wondering if the Nobel Prize Committee would be calling soon?
Yeah, it's like, look at this, actually, we have found something. And then very quickly realised that, unfortunately, I'd discovered my own sloppiness rather than something going on in the universe.
Something I think a lot more people can relate to than just getting a Nobel Prize.
That's very true.
Now, after this, you moved from science research to science communication. So how did this shift come about?
Yeah, so during my PhD, I started doing a hell of a lot of outreach, and I found that I really enjoyed it. So the first way I got involved with this was essentially particle physics outreach days that we had from the lab. And I don't think anyone will mind me saying that usually these were run on a kind of very ad hoc basis. Somebody would come running around the lab the night before and say, "Oh my God, please, does somebody have something to present to a bunch of school kids tomorrow?" And usually it was, let's roll out the spark chamber. We'll show them the spark chamber. And they're interested in that for about 30 seconds. And then they get bored and you see the eyes kind of glaze over. So doing a little bit of that, explaining particle physics to bunches of school kids who were coming in. And also another thing that came around the lab was a vehicle called Bright Club. Now, Bright Club is a vehicle where scientists explain their research using stand-up comedy, which sounds terrifying to most people, sounds crazy as well, the idea of science comedy. But they used to run sessions in Cambridge, and I got involved with Bright Club. I really enjoyed explaining particle physics using stand-up comedy. And as soon as I started doing this, I realized that I seem to be quite good at this. I seem to enjoy doing this. And I thought, well, why couldn't we run one of these kind of Bright Club type events at CERN and use the kind of pull of CERN and do this? So I set up this vehicle called LHComedy, Large Hadron Collider Comedy. And we essentially did a Bright Club at CERN where a lot of CERN researchers got on stage and they explained their research to local people from CERN who spoke English. And the night went really, really well. People really enjoyed it. It was a great way to engage people who potentially have had a bad experience with science or who think it might be a bit boring, to kind of meet them halfway with a few jokes, a few exciting stories, and to get more people excited in science. And I think once I started doing a lot of outreach, I realized that at CERN, obviously everyone is really, really good at physics, but I realized I was probably middle to lower of the pack at CERN, which, probably is a good place to be in terms of physics. But I realized that I really enjoyed doing the outreach and I was quite good at it, whereas other people hated doing it or weren't very good at it. So I moved into doing more and more outreach a lot of the time. And that's kind of how I got into it. And I've just continued doing that ever after and enjoy doing it more and more.
Lovely. And so what sort of things do you get up to now?
So now, as you could probably see in the background, I have a YouTube channel called Bad Boy of Science, where I explain particle physics, try and break it down for lay people, make it more accessible. I also have a show called Hunting the Higgs, where I essentially take school-age audiences and mixed audiences of adults and children through all the steps of the scientific method to discover a particle for themselves. So instead of sitting and listening to me prattle on about particle physics for an hour, I actually lead them through all of those steps. They do a bunch of app-based games, physical activities, mental-based activities to actually discover a particle for themselves by going through all those steps of the scientific method and performing well enough to be able to discover a particle for themselves. So doing shows at science festivals and in schools, YouTube, blogging, writing, talking to other people. And I also tutor still physics and maths, which helps keep my eye in, as Jacob said, because if you drop the ball for a month on your Feynman calculus, it very, very quickly rusts over. So
there is that muscle memory, though. It comes back fairly quickly once you start flexing it again. But it's something you do need to practice. And now, is there a sort of something in particular that you hope your audiences take from your events? Is it like a sort of common aim you have for them, or is it just sort of entertainment that you're looking for?
So the entertainment is important, but what I found when I was looking around and creating Hunting the Higgs was that there's a lot of brilliant science shows and science outreach vehicles that teach people about science, and they do it really, really well. But what I found is there's not a lot of vehicles that get people to actually do science for themselves and learn the scientific method. So what I wanted to do is make them do it for themselves, show them that they could do it for themselves, and show people that they had a place in science if they wanted it. So I wanted to show everyone that they have a place in science, that they can get involved if they want to. And I also do enjoy the entertainment aspect, because I think there's an awful lot of people out there who have had a bad experience with science. Maybe they found it boring at school. Maybe they had a really bad teacher. Maybe they got bad marks in their exams and now they just think it's too hard. It's not for me. And I feel like if you can offer a little bit of entertainment, an interactive game, a few jokes, some science-based songs which are involved in the show, you can help to draw back that audience who have potentially a little bit scared of physics, think it's too difficult, think there's too much maths involved. You can get more of those people involved. I think a lot of science outreach vehicles can end up preaching to the choir. So there's a lot of people who will just come to anything. They're really interested in science already. They will already come. And I try and focus on that kind of audience that's just off to the side, who might be willing to come if you can meet them with something that kind of gets halfway. So a little bit of entertainment, a few jokes. So I try to make it entertaining. I try and make sure they go away having learned something. So learned about the scientific method and learned that they can apply that themselves and in their everyday life. And when I'm presenting things, I always try and relate it back to their everyday experience. So if I'm talking about particle physics, I'll talk about MRI machines. If I'm talking about CERN, I'll talk about the creation of the World Wide Web, something that people use every day. So something that we used at CERN to analyze data, to communicate between scientists, is now something that you use every single day to research things, to answer questions, to talk to your friends. I try to make it applicable to their everyday lives as well. So making things applicable to people's everyday lives, meeting them halfway with some entertainment, and allowing them to essentially power up by learning a new skill, the scientific method, and how they can apply it. I think these are things that I try to get across in my outreach, which is maybe slightly different to the way some people do it.
I think it's lovely. I think it's very important to show that science is a very broad church, both in terms of the subjects you can study and exactly what you're doing. You know, we've talked today about the engineers who make the stuff, the theoreticians who have the big ideas and do the calculus. There's huge amounts there. It's very important to show that. Yeah,
it's important. It's important that people realize this, because some people are very hands-on. They are very good at understanding how things work, and some people don't like that. They just want to think about the more abstract maths. There is a place in physics for all these kinds of interests. So never think that you're not the kind of person who can go into physics. As Jacob very nicely puts it, it is a very broad church, and everyone can have a place in it if they want it.
So what do you see the role of science communicators to be, such as yourselves, to be? And is it something that you feel every scientist should be involved in?
So I've thought about this a lot, and I don't think everyone should be involved in it if they don't want to be, because obviously some people don't want to do it, they don't enjoy doing it, some people are not good at it. You know, we have the stereotype of the kind of mad crazy physicist, or someone who just looks at their shoes all the time. Some people are like that, and they don't like being in front of crowds, and they don't want to be a science communicator, excuse me. That's perfectly fine. But I would like, as a science communicator, I see my role as trying to get people more excited about science, right? And I would like more people to do this. Particularly, we talked last week when I was in at the Cavendish. I'd like to see more scientists from the Cavendish who are interested in doing it, doing science communication, because sometimes people who are working at the Cavendish are the best people, or sometimes the only people in the world who understand the thing that they're working on. So you will never be in a better place to do science communication than working at the Cavendish. And I see my role as kind of trying to excite more people to do science communication and be interested in science. I think that's the role of the science communicator. Now, more wider than that, if you're talking to general audiences, people who are not going to come into physics, I think a lot of scientific projects, take the LHC, for example, are funded with taxpayer money. So I think there's also a right for the audience to understand where their money is going, right? And we have to be able to explain and justify where money is going. So I think that's very, very important. And it helps to have the public on side. If you're going to ask for 22 billion, for example, just pulling that number out of thin air, no, I'm not, for a new particle collider, for example, it helps if you have some goodwill with the public, and they understand what you're looking for, why you're doing it, and they understand the spin-off benefits that they get out of that, the World Wide Web, smaller MRI machines, you know, more amazing magnets, whatever it might be. It helps to have them on side and to show them the benefits that they can have. So I think telling people what they're getting out of science and getting people excited about science, that's the key goal.
And you touched upon this, but you think there are any problems facing particle physics in particular that better communication could address?
Yeah, I mean, that's a very loaded question you've come with there. So yeah, I think that the answer is of course yes. So obviously, at the moment, the big discussion in particle physics, there's a lot of people who say kind of particle physics is dying. You know, particle physics is coming to an end, and that is not true at all. But this is something we hear very often. So the LHC, the Large Hadron Collider, did not find as many new things as we hoped it might. So we found the Higgs boson, but we didn't find things like supersymmetric particles. We didn't find extra dimensions. We didn't find micro black holes, which a lot of people said they might do. So some people feel a little bit shortchanged with what we found at the Large Hadron Collider, which is totally understandable. So when you come back and say, I would now like $22 billion to go build a new machine, people say, well, are you going to find loads of new things this time or not? Do you know exactly what you're looking for? And I think maybe when we built the Large Hadron Collider, science communicators fell into a little bit of a trap. They explained these amazing things that they wanted to find, these specific theories that the particles related to them that they wanted to find, like supersymmetry, for example, or micro black holes. And they didn't explain just how amazing the Higgs boson that they actually found is, and how if we found it, we would have to spend the next several decades building new machines to study it in detail. We fell into that trap. We didn't make that clear. So now we're kind of, and I don't blame people at the time for that, because, you know, they were very excited about their particular area of research. But we're now in a situation where we're kind of almost cleaning up that science communication mess and trying to convince people that despite having found all those things we thought we might find, that we still have good justification to go further. That's the kind of problem in particle physics at the moment.
So is there a sort of an elevator pitch message you think that particle physicists should be sharing? Or is it too complex for that?
No. I think there is. Obviously, it's very, very complicated. I'm making a big, long video about it right now, which will come out next week. I'll just flag that up. But I think the elevator pitch is that we need to study the Higgs boson in detail. This is an incredibly unique particle. This is the first spinless scalar particle that we've ever found. It's the only one that exists in the Standard Model. It's incredibly central to the Standard Model. There's something like 19 free parameters that we put in by hand into the Standard Model of particle physics. And the Higgs boson is linked to the vast majority of these. So all of these open questions in particle physics, why do we have 3 generations of particles? Where does flavor come from? All of these problems are linked to the Higgs boson. So understanding the Higgs boson is an incredibly, incredibly important thing to do. And we need to build larger colliders to produce more of these particles and study them with greater statistics. Now, this is very similar to what we did in the past. So we discovered the W and Z boson, which control the weak interaction, for example, in the late 70s, maybe 80s. And then we very quickly switched from proton collisions or proton-antiproton collisions to building the Large Electron-Positron Collider, which is an electron-positron collider to study those W and Z bosons in exquisite detail. So now we've essentially done the same thing. We've discovered this new particle, the Higgs boson, and it's now on us to build larger machines to study it in detail. We have to repeat that cycle. We can't just find something and then say, yeah, well, it probably behaves like we think it does. Like, we actually have to study it in detail. And I think the elevator pitch is that if you've discovered this amazing, unique new particle, this new probe of the universe, and it's linked to so many open questions in particle physics, if you now decide not to study it because it costs $22 billion, James Webb costs 10, by the way, if you're not going to study it, then what the hell is particle physics for? We might as well just pack up and go home. So, yeah, I don't understand the reticence to do this. The $22 billion sounds big until you realize these projects run for kind of 40, 50 years. And then suddenly it's not such a big number. And it's spread over many, many nations as well. So you can make the number sound scary, or you can spread it out and make the number sound really quite manageable. But I think in particle physics, we haven't made that case clearly to the public about the importance of the Higgs. And mostly that's because it's quite difficult. There's a lot of things that you have to understand and learn in particle physics before you can understand that case. But I think we need to do a better job of it. And I'm going to try over the next few weeks to make some videos explaining that case, because the message that particle physics is dying and that particle physics are just money-grabbing weirdos who want to sit in their, sit in their jobs and build larger colliders is a very simplistic message, and it's very easy for people to digest. It's much more difficult for them to get enough feel of particle physics to understand why we're actually doing these things. And it's much harder to push back. I find a lot of the people who kind of rag on particle physics, it's a very similar message we see in other areas. This kind of contrarian message that the experts are biased, they're trying to protect their funding streams. We see this in climate, we see it for vaccines, we've seen it for everything else. And I think this has kind of bled over in a lesser form, in a less impactful for society form, but nevertheless in the same form into particle physics, where you can put this easy message across that experts are not humble, they're lazy, they're biased, they're just protecting their money. And I think we need to push back against that idea by getting out that more positive message and explaining exactly what we're doing and why. And that's what I'm going to try and do.
So that's your mission for the near future.
For the foreseeable future, that's right, yeah.
Yeah. Excellent. Well, thank you very much, Sam. I think that's all we have time for on this stage. But thank you so much for your time today. It was fantastic to talk to you. As always, if you'd like to learn more about what we discussed in this episode and more generally about our work at the Cavendish, please have a look at the show notes or go to our website www.phy.cam.ac.uk. If you have any questions you would like to ask our physicists, head to our social media and tag us with the hashtag #PeopleDoingPhysics. And we'll also put the links to the Bad Boy of Science YouTube channel, of course, on the show notes. Please do go and have a look.
That's very kind of you. Thank you very much.
This episode was recorded and edited by Chris Brock. Thank you for listening to People Doing Physics. We'll be back next month.